Hello, everyone, and welcome back to Particles in a Box, episode number 2. Today, we're going to be talking about kinematics. Okay, so I often like to start off with some sort of quote or some sort of quirk. Today, we have I thought I should study physics because it's fundamental to all science, and this is definitely true. Physics is definitely a foundation for chemistry and biology, and other sorts of sciences as well. That statement can definitely apply too. The reason why I put that up there today is because kinematics is it deals with motion, right? And one of the big branches of physics is dealing with motion. Okay, and kinematics is the fundamentals to that motion. Okay, we're going to be dealing in kinematics. You deal with a lot of assumptions that are put into these problems, as you'll see as we go forward. Whereas farther down the line, we'll use fewer and fewer assumptions. So this is just an introduction into how things move, is basically what we're going to be discussing today. So overview. First, we're going to talk about the difference between vectors and scalars. Then we're going to talk about position. Then we're going to talk about velocity, then acceleration. Then we're going to do some derivations. And then we're going to be doing some one-dimensional motion problems. We're going to be using one-dimensional examples for the problems this time. We'll be doing two-dimensional and three-dimensional motion in a future episode. But I will be showing you a lot of these equations in their three-dimensional forms. That way you can see them. And so then when you have to apply them down the line, you're not like, oh my gosh, I'm dealing with stuff in 3 dimensions. I think that sometimes people do a little bit of a disservice when they're teaching things in 1 or 2 dimensions where they don't even like hint at that there's like a 3rd dimension that can be used. So to me, it's good to expose people right away to things they might be dealing with in the future, right? And we can start off with simpler problems, and then we can increase the difficulty as we go forward. So first off, we've got vectors and scalars. So scalars. The definition of a scalar is that it has a defined magnitude at a defined point in space. Okay. So examples of this are distance, speed, mass, energy, time in a non-relativistic sense. If you're not familiar with relativity, don't worry about it. Time is a scalar, and temperature. Okay. A common functional form is that you just have some function of x, y, and z, and that the magnitude of that function is the magnitude at each defined point in space, x, y, z. So if we go over here, right, and we want to talk about an example of a scalar, right, you can pick a point, right? We'll say, okay, so we'll go to 2, 7, right here's a point, right, and that might have a magnitude of 2, for example, okay? Or we can come down here to 6, 0, right, and this might have a magnitude of 3, okay? So you can have scalars that are defined as points, which is what we're going to be dealing with, right? When we're doing kinematics, we're treating things as point particles. So like it's like each individual point, right? So like this object can have a mass of 2, it's located at this point, right? This object has a mass of 3, it's located at this point, and then over here we can have something of mass of 4 located at this point over here, right? So that's kind of what we'll be dealing with. In the future, right, things can become a little bit different, right? Where you can have a region, right? You can have a circle, right? And this circle, right, has a mass, right? And it can have what is called a mass distribution, right? Where the mass inside of this circle, right, it can't be constant, right? There could be more mass. There could be more mass out here at the edge, right? There could be more mass here in the middle. But that's for future. But just so you know, in the future, you can have points that have magnitudes, but you can also have like a region or a distribution of mass. So that's the basics of scalars. Vectors. Vectors have a magnitude and a direction and are defined for each point in space. Examples of this are displacement, velocity, acceleration, force, and momentum. So the first thing you want to recognize is that vectors come in different forms. Whoops, I want to go forward. Right, you can do the Cartesian representation. Right, this is the most common way to write a vector, where you have some function times I hat, some function times j hat, plus some function times k hat. We'll get to what these hats represent here in a second. Or you can write it in polar form, okay, where you have some overall magnitude and then some angle, and then if you're in 3 dimensions, you can add on the z component. Okay. The important thing to remember here is that the polar representation is technically just r theta. If you include the z component, it is called cylindrical. That's just something that you should keep in mind. So what is up with these I hat, j hat, and k hats, right? So what those are is that those are unit vectors in a particular direction. So what do I mean by that? Is that I hat is the vector that just goes of magnitude 1 that goes straight along the x-axis. That is I hat. And then if you go straight up 1 unit, that is j hat, okay? And the reason why we do this, right, is that you can write vectors in terms of these 2 unit vectors, right? Because if you multiply by a scalar out front, right, that just increases the magnitude of the vector, right? So if I multiply by 8, right, well, okay, this is now my vector's out here, right? But if I multiply by 7, right, then my vector is 7j hat, which is up here, right? And then you can add these 2 things together to get some other vector, right? So if we add those 2 vectors that we just made together, right, we get some vector that goes out here, okay? And then so that's, you know, j and I, right? If you added in k hat, right, k hat would be coming in or out of the page. So that's three-dimensional aspect. If you're dealing with r and theta, right? How that works is that you can have some sort of vector going outwards, right? This is going to have some magnitude r, right? And then you have some angle theta that goes up from the x-axis and it goes counterclockwise, okay? So if you're right along the x-axis, that's 0 degrees, right? If you're up here at y, right, on the y-axis, that's 90 degrees, 180, 270, and then you can go back around. The important things that you want to keep in mind is that sometimes it is easier to use one form over another, right? You kind of, based on the context of the problem and what you're solving for, might be easier to find your vector in polar or Cartesian coordinates. The other thing is that sometimes people write vectors as like a comma b, right? And this looks like a point even though it's a vector. So depending on what textbook you might be reading or what professor or what teacher or what book you're reading, right, they might write vectors in slightly different ways. So do consult the chapter in your textbook on how they write vectors, so that works out. The other thing you want to keep in mind is that vectors in Cartesian add and subtract intuitively. What do I mean by that? Okay, so if we have a vector a1, a1, b1, right, and we have another vector a2, b2, right, and I want to add these 2 vectors together, right? How that's going to work is that it's just going to be a1 plus a2, comma, oops, that is not very good, b, comma, b1 plus b2, okay? So what that means, so what I mean by intuitively, right, is that the x component adds and or subtracts with the x component, and the y component adds or subtracts with the y component. You don't need to cross over, and so then you just get this, right? It adds the way that you want them to. Okay, that is not true for polar. Okay, these polar vectors do not add intuitively. For example, if we go to the next slide, right? So for example, right, let's say I've got a vector 1, 1, right, in Cartesian, and I've got a vector 2, 1 in Cartesian, right? The resulting vector, right, is going to be 3, 3. Okay, perfect. Okay, but if I do the same example in polar coordinates, for example, right, the first vector that I drew is 1, 45, right, 45 degrees. Okay, the second vector is 2, 45 degrees, right? Okay, so if I add these like I did in Cartesian, right, I should get 3, 90. Whoops, that is not 90. Okay, so that vector would be right here. Okay, well, hang on, that's a little bit of a problem. We just got a different answer compared to when we added vectors in Cartesian, right? And it is a problem because this is not the right answer right here. Do not do that. vectors in polar form, you cannot just straight up add the components together. That will get you the wrong answer. How you add vectors in polar coordinates is more complicated and is beyond the scope of this video. So if you, for whatever reason, need to add vectors in polar at this stage, it's just better to convert them into their Cartesian forms rather than trying to add them by hand. And you'll see an example of me converting from polar to Cartesian coordinates in one of the example problems. So if you're curious about that, that's coming later. So next up, we have distance and displacement. Okay, so displacement is a vector quantity. Okay, what that means is that displacement is independent of the path taken. That means that only the final position that you're taking, the final and starting position that you're taking into account, are the only two measurements that matter. Okay. So first off, just a quick definition. So right here we've got delta Q. Okay, Q is just some quantity. Okay, any quantity. It could be a mass, could be a time, could be a speed, any quantity. It's just that delta Q is defined as the final measurement of that quantity minus the initial measurement of that quantity. Okay. So when we come down here, we define our displacement vector. What we get is we get the change in the x position times I hat plus the change in the y position times j hat plus the change in z position times k hat. Okay. If you want to put this into polar form, what you do is you just use Pythagoras to find the total magnitude of the vector, right? And then you can do the change in y over the change in x, take the tangent inverse of that. And then it's just delta z z hat in polar form, right? So if we go forward, right? So for example, right, is you can have some sort of vector, right? Well, say we got 5, 5, right? So right, in Cartesian, that's 5, 5, right? And polar, that is you have to square both of them, right? So that's 5 squared plus 5 squared, and then you got to take the square root to find the magnitude, right? So that's 25 plus 25 is 50. So the length of that vector is the square root of 50. And so in polar, we'd have square root of 50 comma 45 would be our vector, right? So I actually just explained how to convert between Cartesian and polar by using that formula conveniently enough. So if you like, this is how you find r, right, and this is how you find the angle. So that's pretty nice and dandy. Oops, go back real quick. So displacement, right? Final minus initial, right? So if you have a point over here, right, and a point over here, right, your displacement, if this is the final point and this is the initial point, right, this is your displacement vector, right? And that goes for any 2 points, right? You can go from over here to over here, right? That's, you know, that's a displacement, right? It's just pointing you to the, it's pointing you from your initial spot to your final spot. So next, we have distance. So distance is a scalar quantity. It's not a vector like displacement. It's the length traveled over an entire path and is dependent on the path taken. Okay. Down here at the bottom, I have the equation for the arc length of a line using derivatives and an integral. Just keep in mind that this is assuming that you have a function for x, y, and z in terms of t, right? If you had so like x is equal to some function of t, right, is what this formula relies on. If you had like a formula of like y equals some function of x, for example, right, that's not gonna, it's gonna change this formula a bit slightly. Okay, since we're dealing mostly with position as a function of time, right? We're not going to worry about this other one, but I just thought I would throw it up there for those of you that are curious. So over here, so what is really the fundamental difference between displacement and distance, right? So the best way I can illustrate this, right, is if we start down here at some initial position, right, and we end up over here at some final, and we go to this point, we go this point over here, right? So we go from here this point and we go to that point, but then we go from this point back to our original point, okay, right? So this point is our initial point, but it's also our final point as well, okay? And so if you do the math, right, our initial point, our final point are the same, so our displacement vector is equal to 0. Is equal to the 0 vector, okay? But our distance is not 0 in this case, right? You have to account for the distance that it takes us to get to this point, and then you have to add that to the distance that it takes to get back. So our total distance is d1 plus d2, right? It's the distance that it took us to get there and the distance it took us to get back. Another example of this, right, is if you start down here, right, and you go to this final point right here, right? Our displacement, right? Okay, bam, that's our displacement. But say we take some really wonky curve to get there, right? Okay, so our displacement is our final minus initial, right? But our distance is not the same, right? You have to calculate the distance of this entire squiggly line path to get there, right? So that is what the difference between distance and displacement is, right? Displacement, you can kind of think of it, right, as if you're like a bird, you're hovering above the earth and you're just flying straight there, right? But distance has to take into account, oh, you're on the ground, right? You got to dodge maybe some mountains or some hills or something to get to your final position. Next up, we have velocity and speed. So velocity is a vector quantity. The average velocity is defined as your displacement vector divided by delta t, or some change in time. So you have some change in position, divide that by some change in time. You just need to make sure that your final position point corresponds to that final position time, right? So you need like xf, comma tf, right? Like this final x position needs to be the same as your position would be at the same final time, right? You can't just be like some random arbitrary stuff. That's your average velocity between 2 points. But there's also instantaneous velocity, where if you take the derivative of your displacement with respect to time, and you take the derivative of each component with respect to time, you get the instantaneous velocity. Okay. So the key thing with velocity is that it's a vector, right? So so just make sure that when you're calculating velocity, you're using displacement, right, instead of distance. Otherwise, you should be all right. Speed, well, speed is a scalar quantity. Speed is distance divided by time. And that's really all there is to it. It's a scalar quantity. You now have distance, which is a scalar instead of a vector, so that's how you get speed. Not much to add on to that. So acceleration. So acceleration is also a vector quantity, like displacement and velocity. Your average acceleration is your average velocity divided by some change in time. It is also the same as doing your total displacement divided by the change in time squared. And your instantaneous acceleration is the derivative of your instantaneous velocity with respect to time, or the second derivative of your displacement vector with respect to time. So in the first part here, right, I've got your change in velocity with respect to time here vector, and then over here I have your second derivative, vector. The one thing I'll say here, right, is that yes, there is technically you could say there's technically an analog to acceleration. Like there's a scalar acceleration that exists. The problem is that that's not really particularly very useful in really any situation that I can think of off the top of my head. Part of the reason for that is that force is a vector, right? And force is equal to mass times the acceleration. I'm sure many of you have seen this equation before. So since acceleration is related to force, and force is a vector, acceleration is also a vector, there isn't a whole lot of a good reason to use the scalar version of acceleration. So, kinematic equations, okay? We're going to be doing some derivations here. Now, when some people hear the word derivation, they kind of freak out and go, oh my gosh, we're going to be doing some derivation. This is going to be really difficult. And yes, derivations definitely can be difficult. That is definitely true. But ultimately, derivations is where the physics truly lies, right? You take in some initial variables that you know, and you use logical reasoning to then, with those variables, get out a new variable or a new answer or a new quantity, right? And that's what physics is about in a lot of respects, right? Is taking a bunch of stuff that you know and then trying to find something that you don't know, right? And derivations help us do that. And the derivations also are generalized, right? They're not just related to one specific situation, right? They can apply to many different situations by using the same assumptions. So the equations that we derive here, right? You can use them for hundreds, thousands, millions of different problems, okay, where the assumptions are valid, okay. This also brings up another good point, right? In that your equation that you get out of your derivation is only as good as the assumptions that you put into it, right? So you need to understand that these equations are not valid in every single situation, right? And that you need to know when the equations can be applied. That isn't necessarily going to be a big deal in like the practice problems that we're going to be doing today. But as you get farther and farther down the road in physics, right, knowing when the equations that you actually have can be applied are important, as by using the wrong one, right, will get you the wrong answer. So and that quickly can become a problem. So first off, we are going to get position from velocity. Okay. So the first thing I want to point out, right, is you want to, whoops, looks like this got cut off a little bit. That's a dx right there. Is you want to remember that if you add two functions, if you're integrating two functions that are added together, right, you can split up the integrals and add the integrals together. Okay. The reason why this is important, right, is that we've been writing our vectors in addition notation, right? We've got a I hat plus b j hat, right? So what this means, right, is if you want to integrate this, right, well, you can split this into the I component integral, and then you can add it to the j component integral, right? So yes, I'm writing vector here, right? To show you that you can do this on all three or all two or three components of your vector, right? Ultimately, you're going to use the equation, right? You're going to use the equation. You're going to do your x component, and then you're going to use the equation again. You're going to use your y component. Okay, you're not really going to be doing the components together. But I want to use the vector notation to show you what is a vector and what is not. So you're really only applying this when you're using, again, one component of your vector. But you're going to be applying this 2 or 3 times depending on how many components of the vector you have. Okay, so what we're starting out with is that we have the definition of instantaneous velocity here, the derivative of your displacement with respect to time. This is also called a differential equation. Okay, you have a derivative that is equal to some sort of expression. Okay, some of you probably have heard of differential equations, and then you go, oh my gosh, those are hard to solve. Well, some are a lot harder to solve than others. There'll be plenty of very hard examples of differential equations as we go on, but for right now, we get the simple cases. So what we do is we just multiply this dt over to the other side. You can do that, and sometimes physicists and mathematicians like to poke jokes at each other. Physicists can have a reputation of just doing things mathematically that aren't necessarily super well defined or have like a super large precedent associated with them. But the counter argument to that, right, is that physicists were trying to describe reality, right? So if we do something mathematically that might seem a little bit dubious, but it ends up matching experiment and ends up matching reality, then it worked, right? Like if it matches experiment at the end of the day and it matches what we observe in reality, if you did something a little bit dubious to get there, that's kind of all right. You can then go tell your mathematician friend, hey, this matches reality. Go find some proof of it somewhere, right? So it's just a back and forth between physicists and mathematicians, as we like to have a little bit of fun. So what we do here, right? We multiply the dt over, right, and then we can integrate. We can integrate both sides, right? On the left hand side, we have our time bounds. We have our initial time and our final time. And then over on the right, we have our initial displacement and our final displacement, okay? Then we assume that velocity is constant, okay? The reason why we need to make this assumption is that we get out this expression right here. This expression is not valid if velocity has a dependence on time, right? Like if our velocity vector is equal to t, for example, well, then we're going to get out t squared, right? So that's obviously not what we get over here, right? So we need velocity to be a constant. We'll just say n, right? It needs to be some number, and you can get this result out, right? So antiderivative of v times dt, right? V times t plus a constant, evaluated at t1 and t naught, and then you just get the vector d, right? If you integrate with respect to dd, right, you just get the vector d out plus some constant evaluated at that. You're going to let your t naught equal 0, right? So this, so the constants drop out, and then you get that the vector vt is equal to the final displacement minus the initial displacement, and then you can rearrange to solve for your final displacement. Okay. Click this next slide. So next up, we are going to grab acceleration from velocity, right? Again, we're going to start off with the instantaneous acceleration, right? We're going to multiply over a dt, right? We're going to integrate both sides like we did last time. This time, we're going to assume that acceleration is constant, and so that gives us our acceleration vector times time plus constant evaluated our points, right? And then dv just ends up becoming v plus some constants. Right, and then you get your nice long expression down here. We let t naught equals 0 again as well, and then you get down to here, right? So again, basically you're doing the same derivation steps and then logical reasoning as you did with the previous example, except, right, we're dealing with acceleration velocity now instead of velocity and displacement. So next up, we have position from acceleration and velocity. Okay. So first thing is on the previous side, we derive this, so we know this up here. We also know that the final velocity is equal to the instantaneous velocity evaluated at tf. Okay. You can also drop the subscripts and just say that the velocity at some time t is equal to the instantaneous velocity evaluated at whatever time. So that's what allows us to set this first part equal to the derivative. Here is if you just drop a subscript and you just make it whatever time t, right? You can set the first two equations equal to each other. Multiply over our dt like we have been doing. That's going to give us an integral. We're going to call our initial time t. We're just going to plug in 0 this time, and we get dd over here. Okay. Again, you need to assume that acceleration is a constant. So acceleration is equal to a constant. Okay. Our initial velocity, that is already a constant. That does not have a time dependency on it. That is just some velocity, right? It's not arbitrary. It is defined as a constant. So when we do our antiderivative, right, we get 1/2 times the acceleration vector t squared plus our initial velocity vector times t plus some constant, evaluate our final time and our initial time, and then like before, right, we just get our displacement out, evaluated at the final displacement and the initial displacement. So we plug everything in, right, and we get down to here, okay. And so then you can do delta d, or you can separate out your initial and your final. Okay. So I'm going to put a star next to this equation here, right? This is an equation in kinematics that you're going to be using a lot. Okay, right? It takes some constant acceleration, and you have some initial velocity, and depending on how long you go, you go some displacement. Right? This is very versatile, right? It's a lot more versatile, right, than this equation back here, because right, if your acceleration is 0, for example, right, say that your acceleration goes to 0, right, well, this whole term just goes to 0, right, and you're left back with what we derived, right? I derived before. So that checks out very nicely. Some of you might recognize this as well. This is an equation that is on the AP Physics 1 equation sheet. So if you're in an AP Physics class, you'll be using this a lot. It's also on your equation sheet. So if it's on that equation sheet, most of the time that means it's an important one, and this is one that you should definitely have memorized. Before I go on to the next slide, I suppose this is a good point, good chance for me to talk about what equations do you need to memorize, and which ones do you not. And I think that this is a common place where people go wrong in physics, is that they think that they have to memorize every single equation. Physics is not something where you can just memorize everything, right? There are a few people that I have known that have gotten away doing that, but for the most part, most people that I know who do physics, myself included, kind of just do it intuitively, right? Like we just have some sort of like experience and just some sort of ability to kind of just like think through it logically, right? And get to where we need to go. So in relation to that, right? Oftentimes there's like 3 or 4 equations on the unit that you're on that are absolutely like you must know these, right? So like this is an example of one of them, right? And there's going to be like 2, 3, maybe 4 of those, right? Where all the other equations that pop up in that chapter, right, most likely are offshoots of one of those 3 or offshoots of one of those 3 or 4 other equations, right? Where it's a special case, or there's some sort of niche, or there's like some sort of major exception that is coming up, right? And so oftentimes what you can do is that off of those 3 or 4 main equations, right, you can derive the other ones relatively easily in like 2 or 3 steps, right? So again, that can take you like 30 seconds, right? Most of the time. So it's kind of, if you have good logical reasoning skills, right, you can get away with memorizing fewer equations. And so yeah, we're right. You don't need to focus on memorizing every single step, every single thing, right? Focus more on the general concepts. What are the assumptions that are going into this? What are the variables that are going into this, right? And then let your logical reasoning kind of guide you through the process and guide you through the steps. And most of the time, that should get you in the right direction, if not the right answer. So going to our next equation. I hate how it does this sometimes. There we go. So we have our equation that we just derived up here, and then we also have a previous equation for final velocity from acceleration, right? What we can do is we can solve for acceleration. We can then plug that in over here for our acceleration, right? And then we can just go through algebraically, right? And keep in mind that these two things are like terms, so that just becomes positive 1/2, and you can get your final displacement or your change in displacement without acceleration. Acceleration right here. That's one of the other things, right, in kinematics, right? Like you've got acceleration, you've got final velocity, you've got initial velocity, you've got time, you got final displacement, and you've got initial displacement, right? And so oftentimes it's given or implied 4 or 5 of those variables, right? And it's up to you to find the other 1 or 2, right? And so what we need to do is we need to use like the 3 or 4 equations that we have memorized, right, to eliminate one or all of the variables that we don't know, so that we can solve for a variable that is a little bit easier to get to, and then we can use another equation to get the last variable, right? So you'll see that as we do practice problems. But this is why we need different forms of what is essentially the same equation, so that we can find things so we can find something from something that we actually know. So next we're going to do position without time. So we have our good old equation right here. We also have our final velocity equation up here. This time we're solving for time. And then we can plug time back into this equation up here. So we get time from this equation, which we plug in over here. We have this right here. We plug them in, and then we end up simplifying a little bit here, right? We pull our accelerations out, we leave our velocities inside. One thing I want to point out here, right, is that when I write 1 over a vector, right, keep in mind that this is really a component of the acceleration vector, right? It's not the whole vector itself. It's definitely mathematically dubious to just do 1 over an entire vector. That isn't something that I know is very mathematically well defined. But again, if you're just using a component, right, and you're just using one part of the vector, right, that's totally fine. So do keep that in mind. Don't be accusing me of telling you that you can divide by a vector. You definitely cannot do that. So then what we end up doing, right, here is we end up gathering, going from here to here, right, we end up gathering some terms, right? We multiplied both sides by the a vector, right? So that's why the a now pops up over here on the right-hand side. We get rid of the a's over here on the left, right? We recognize here that these two terms right here go to 0, right? And that this term and this term right here are actually alike, and that one is going to give us the minus 1/2 v initial squared right there. We can multiply through over by our 2, right? And then we can do some algebra to get ourselves down here to our final equation. This is another one that I'm gonna start. It's also on the AP Physics 1 equation sheet, where you can get final velocity from acceleration and position without knowing the time. Again, a pretty big equation, and yeah, it is going to be quite useful in many problems. Okay, so now we're going to be moving on to problems. I know this is already a long video, but what I will say about these problems, right, is you don't need to necessarily go through every example. Of course, I would appreciate if you watch through, but you don't have to. As I put these up on the screen, right, I'll try to give you an opportunity to where you can pause the video real quick, so that if you want to try these yourself, you absolutely can. Otherwise, if you're just kind of here to enjoy the show, I'll keep going. But when you try it on your own, right, give your best chance, right? If you get stuck, you can, struggle with it for a few minutes, but then, you can check back into the video if you get stuck, and you can see where you went wrong. I'll probably do a video on like general problem solving strategies and kind of how I approach problems a little bit later down the line. But for now, we'll just kind of walk through things, and maybe we'll kind of pick up on some things that I do that maybe you don't do, and vice versa. So our first question here. I guess the other thing I want to say here before we get started is that at the beginning, right, we're kind of just doing some conceptual questions, right, that don't involve a whole lot of calculations, right? Just kind of like intuitively think about it, right, conceptually, and then as we go on in the problems, right, they become a little bit more and more mathematical based. Of course, with these conceptual ones, right, you can also like use math, right, to help you get to the answer, right? But the idea is that you kind of can just think about it conceptually, and arrive at your answer. So first off, if the average velocity of an object is 0 in some time interval, what can you say about the displacement of the object for that time interval? Okay. So let's remember that average velocity, right, is equal to displacement divided by time. Okay. So if this is equal to 0, for example, right, how can we get this equal to 0? Well, option number 1 is that our displacement is 0. Okay. That seems completely valid. Option number 2 is that our time is infinite. Well, time is not always going to be infinite, so displacement is indeed equal to 0. If the average velocity is 0, our displacement is also 0. The displacement is 0. If the velocity of a particle is non-zero, can the particle's acceleration be 0? The answer to this is it is indeed yes. You can have a velocity and just not be accelerating. That's called moving at constant velocity. And this comes up a lot more when we talk about forces, where you have where you don't have an acceleration, you're moving at constant velocity. But it definitely is possible. Can the equation of kinematics be used in a situation where the acceleration varies with time? And the answer is a no. That is not possible. The derivation specifically stated that we needed to have a constant acceleration. If we don't have a constant acceleration, we are going to be in trouble. It's not to say that you can't ever have something that isn't moving with a constant acceleration, right? If we go back here, for example, right? So to get from here to here, right, we said acceleration needed to be equal to a constant, right? Well, if your acceleration isn't constant and it is varying with time, right? Well, you can just go back to this step of the derivation, right, and plug in whatever your acceleration is as a function of time, and you can get out the right answer, right? So, so that's totally, totally fair. Well, actually, wait a second. Actually, hang on. Do I have that wrong here? Let me go back real quick. Yeah, so you would actually have to go back here. You'd have to go back even farther, actually, because this equation tells you right here if acceleration is constant, right? So so this equation up here would actually be different, and so you'd have to go through this process, this process again, in order to find it. But needless to say, the point I'm trying to make is that you can have something that has a varying acceleration with time, and you can still find equations and describe the motion. You just can't use the equations that we derived. So up next, we have a x versus t graph is made, which has enough data points to be considered smooth. Which of the following quantities cannot be obtained from this graph alone? So again, try it out by yourself if you want. Otherwise, if you're going to enjoy the show, we'll just keep going. So the instantaneous velocity, right, is in this case would be dx dt. X is our position, and so they're using x instead of d, so that's totally fine. I guess I'll mention right here, right, is I used d because you can use d can represent x, it can represent y, it can represent z, right? When people are taught, oh, it's dx dt, right? Well, then some people kind of get stuck in this mentality of, oh, well, it only applies to x, when in reality, no, it applies to any variable that's representing position, right? And so I don't want people to get hung up on that, right? It's just you can use any positional variable. X is a common positional variable that we use, but it is not the only one, right? So don't let the x or the x intimidate you. Is what I'm trying to say, right? Again, this is why it's important to understand what is your variable, right? Like it's not like x, like itself, the letter x, right? It's that x is representing a positional, is representing position, right? Or a displacement or a distance, right? It's not just the letter x itself, right? So you can use other letters to mean the same thing that aren't necessarily x. But anyway, moving back on, the instantaneous velocity, right, is dx dt. which you can definitely get from the x versus t graph. The instantaneous acceleration, right, is the second derivative, right? So you cannot get instantaneous acceleration directly from the x versus t graph. We'll come back to that in a second, but for right now, B is off the table. The displacement some time interval, we have a position with respect to time. You can totally find a displacement some time interval. That is definitely not a problem. If we draw a graph, right, and we have some sort of curve, my axes aren't particularly straight, but that's all right. Right, you can pick 2 points on that curve, and you can draw a vector through them. And so that'd be your displacement. The average velocity at some time interval, yep, you absolutely can. So you can take your displacement, right? You have your 2 times, and you can find the average velocity, no problem. And then the speed, if you can find a velocity, you can find the speed. So the answer here is B. I do want to put a caveat out there, right? Is that right? It's a second derivative, right? And if you give me a function, right, x is equal to t squared, for example, right? Well, I can take the second derivative of that, right? I can tell you that that is just going to be the second derivative of that is just going to be equal to 2, right? So it's like, can you get it directly from the x versus t graph? Sort of, right? But for our purposes, we're going to say that you can't. So yeah, so the answer is B. So moving on to the next question. Again, go ahead and pause if you want to try this yourself. Otherwise, if you're just here to enjoy the show, you can feel free to. We'll continue on. So we have an object moves along the x-axis according to the equation x is equal to 3t squared minus 2t plus 3. And we want to determine a few things: the average speed between t equals 2 and t equals 3, the instantaneous speed at t equals 2, the instantaneous velocity at t equals 2, the average acceleration between t equals 2 and t equals 3, the instantaneous acceleration at t equals 2, and when the object is at rest. So first off, we are going to do the average speed between t equals 2 and t equals 3. So we have our average velocity is going to be equal to, since we have a function of x, we're going to be using x instead of d. So we got change in x over change in t, right? So x evaluated at 3 minus x evaluated at 2 over 3 minus 2. You plug in your numbers, you get out 13. Don't forget to put units on your answers. We're going to be using meters and seconds for this problem, right? If it was a millimeter or something else, make sure to use the right ones. You can definitely get plenty of points deducted on exams and whatnot by not putting proper units on something. So then the instantaneous speed at t equals 2, well, what we're going to be doing for this, we're just going to be taking the derivative, right? We have our function, right? If you take the derivative with respect to time, you get 16 minus 2. And then if you plug in t equals 2, you get out 10. So the instantaneous speed at t equals 2 is 10 meters per second. So, I might be wondering, okay, we found the instantaneous speed at t equals 2. What is the difference between what speed and velocity, right? Well, remember, way back at the beginning, we said that speed is a scalar, right? So we just have a number, right? But velocity is a vector. So in order to give the most complete answer possible, right? You need a magnitude, and you need a direction. Okay, so you need 2 things, right? Because velocity is a vector. Again, sometimes, if you're in a physics class, right, your professor or teacher might not require you to find the direction. They might just be fine with the magnitude. But I've known some that are sticklers and they want you to find the direction. Otherwise, it's one of those things where it's like, well, I'm asking you for velocity, right? If I just wanted the magnitude, I'd ask you for the speed. Again, that's something that if you're in a physics class, definitely talk to your teacher or professor and clarify what the expectation is. But for this, we're going to assume that we need a direction. Okay, is what we're going to assume. So the good part is that in this case, the magnitude is the speed that we just found. So we're really looking for the direction here to finish off the answer to this part. So let's bring this over here. Okay, so what we're going to be doing here is that if you look over here on the right, I've got the red. I've got the red line, right, which is our original function, original function up here. So let's put this box in red, right? And what is happening, right, is that I graphed our average speed from part A here in green. Okay, I did some math behind the background to find out what the equation of that line is, but as you can see, right, it intersects the graph here at t equals 2 and then up here at t equals 3. Okay, but I also have the velocity, the instantaneous velocity here that touches our motion graph here at t equals 2. Okay. So in order to find the direction, we need to find the equation of that blue line, okay? And the easiest way to do that is to use point slope form, okay? If you remember correctly, that there's two different forms of a linear equation or a linear line, okay? You can use slope intercept form, or you can use point slope form. The reason why point slope form is useful in this case is because we know the coordinates of the tangent / intersection point between our velocity line and our motion line. Okay, we know that it occurs at t equals 2, and we know that it occurs at our position evaluated at 2 seconds. Okay, so by using point slope form, we can just plug in those numbers right away, which are 11 and 2. Okay, so we can plug those in right away. And then we can go ahead and solve. And oh, what do you know? Voila, we went from point slope form back to slope intercept form. Okay, cool. So now we're back with maybe something a little more familiar to all of us. And so in order to find the direction, you just take the tangent inverse. You take the tangent inverse of the slope. Okay. Technically, yeah, we maybe didn't need to do all of this to find the direction, but it's good practice to. I also can't talk. To grab this, right, because that is the equation that I used for that I used for this blue line, right? So yeah, and keep in mind, right, that this origin, I don't think that this is actually 0 right here, so that's why the y-intercept might look a little bit off. Is that, yeah, this is not. Yeah, I think this is actually like 1 second right here. So do keep that in mind, why that might be a little bit off. But you take the tangent inverse, right? And that gives you some number and some number of degrees. So the quickest way that we can do this, right, since we know the magnitude of our vector, right, we know that it's 10. We can write this in polar form. So 10 r hat plus 1.47 theta hat. So that's all well and useful, right? But it can also be useful to convert it to Cartesian form. Sometimes it can be a little bit hard for some people to visualize the polar vector, right? So as you can see here, right, it's basically 1 in the x direction, right, and really heavy in the y direction, which makes sense because we're almost at 90 degrees. So cool. Let's move on to the next part here. Okay, so Tommy here. I realized that I made a little bit of a mistake. So you can hear me right now, but the screen's gonna be frozen. And that since we're doing motion in 1 dimension, we don't have a like an angle like 85 degrees for our velocity. It should just be it should just be straight to. It should just be in a straight direction, not some sort of angle offset. So. Yeah, so yeah, that's my bad. The velocity is actually in this case is just straight to the right. So it would be it'd be 10 comma 0. So you can ignore part C. That is my bad. That is me definitely overthinking the problem. So yeah, feel free to discard that. But the velocity is actually just straight. Is just straight to the right. In this case. Okay, but this does actually bring up a good aside though that I do want to bring up, even though I definitely messed up. Is that we are going to be going back here real quick. Let me grab one of our coordinate axes right here. So what I wanted to explain, right, is that in that solution I had r hat and theta hat, right? So I showed you what I hat and j hat were earlier, right? But what is r hat? What is theta hat, right? So r hat, right, is just a vector that points in the direction of our vector, right? So if we have a vector that comes out like this, right? Well, r hat is a unit vector that points in that same direction, but is just of unit length, right? So it's just r hat, right? But if we have like a vector coming out over here, right, then r hat would be something close to that, right? It points in the direction, but it has a length of 1, right? Theta hat, on the other hand, is a little more complicated, right? In that, right, since theta is measured from where we start, right, on the x-axis all the way over, right, theta hat points perpendicular to r hat, right? So in this first example, right, theta hat is going to be pointing to perpendicular to r hat, right? But it also again has unit length of 1. Then over here, right, it would be pointing down, right? So your r hat and theta hat vectors are not the same for each vector that you draw, right? Unlike I hat and j hat, they stay the same no matter what vector you draw, right? Those vectors point in the same direction. R hat and theta hat point in different directions. This is also part of the reason why you can't just straight up add polar vectors together in a way that seems super intuitive, is because the vector directions do change. So that's part of that. Okay, so we're going to continue on. You can ignore this. You can ignore this whole part, right? The direction is really 0 degrees. It's really just 10, 0. Now let me draw that a little better, right? It's just 10, 0 degrees, right? You can ignore this whole part, right? If you're wondering why I did this and why I got confused, right, is because, right, we have time and we have position, right? So yes, the slope of this line is 10, right? And it does form it does have like some angle, right? But that is not the angle angle of the velocity with respect to the problem, right? Because if you think about it, right, so the only direction that we're moving, right, is we're moving on the x-axis, left and right, right? We're not really actually moving up and down at all in this problem, right? We're doing one-dimensional motion, right? So we're just moving left or right. It appears that we're moving in 2 dimensions, right, because we have the time axis on there, right? If we remove the time axis, right, we would just be moving left and right. So what's really going on in the problem is that, well, since the time is greater than 0, right, we are since we're at time t equals 2 and time t equals 3, not necessarily greater than 0. You'll see in a second. But we're just moving. We're moving outwards, right? We're moving in the positive x direction, and we're just moving in that positive x direction faster and faster as we accelerate in that direction, right? So the velocity is still in the positive x direction, which is 0 degrees. So yeah, what I still said about like speed and velocity and like you needing a magnitude and a direction for velocity, right? It's still true. You just don't need to do this do this whole thing. So we've got the next part. We're gonna find the average acceleration between time 2 and time 3. Right. So you get average acceleration is the change of velocity over the change in time. You do your instantaneous velocities at 3 and 2. You subtract them, right? You end up getting 6, and then you want to put your units on that. So that is meters per second squared. If I can write, oh boy, write that a little bit better, that would be ideal. And so we want to find the instantaneous acceleration at time t equals 2. So you take the derivative of our instantaneous velocity with respect to time, right? And that's just 6. So that's just showing that our acceleration is constant, and that's 6 everywhere. So I added the black line on the graph. That is our acceleration. It is 6, and it is constant at all time. So part F. What is the object at rest? Okay. So what it means for an object to be at rest is that its velocity is 0. Okay. So if you look at our instantaneous velocity graph, which is the purple line, okay, that is the 16 minus 2, right there, right? You can see that it is 0 approximately right here, okay? What that also corresponds to is, since we have a quadratic equation, right, that corresponds to the minimum of our motion graph, okay? So that corresponds to the minimum, right? So, because again, whenever you have a derivative equal to 0, that is a minimum, maximum, a minimum or a maximum point, and in this case, it's minimum point. What I decided to do here, right, is we want our instantaneous velocity equal to 0. So I wrote down the generic form for a quadratic here, right? And so there's a couple of things that I wanted to do and demonstrate in this part here. First of all, right, is I use C1, C2, and C3 for a very specific reason, right? Is that we had an equation earlier, right, that had 1/2 AT squared, right, plus VIT plus DI, right? But then there's the standard polynomial form of a quadratic equation, right, which is a squared, well, whoops, not a squared, which is a t squared plus bt plus c. Maybe you know where I'm going with this. Maybe you don't. But you have an a here, and you also have an a here. These a's are not the same. I'm going to say that again. These a's are not the same, right? You have a 1/2 out here as well, right? This a is the acceleration right here. This a is the entire coefficient on your t squared, okay? So, when you're plugging stuff into the quadratic formula, for example, you need to be careful about what you're plugging in. If you just plug in your acceleration, you are going to get the wrong answer, right? You can multiply through by you can multiply by 2 to get rid of this. But again, just do your due diligence. Do your due diligence and make sure that you're careful when seeing these A's pop up, right? So that's why I wrote C1, C2, and C3, right? So you can't. It's a lot harder to get confused. Let's go back to green. So we end up taking the derivative with respect to time, and so then we get that 0 is equal to this, and we can solve for time. So if you look, so for example, this is equal to negative b over 2a, right? And it's surprising the amount of people that I find that don't know that the minimum or maximum point on a graph has the independent variable equal to negative b over 2a. So if you have a quadratic function and you need to find the minimum or maximum point, right, your independent variable quantity is just negative b over 2a. So when we use our example, right, we've got negative of a negative 2 over 2 times 3. That is 1/3. So we know that at t equals 1/3 or 1/3 of a second, right, that this is 1/3 comma x of 1/3. Okay. So so do keep that in mind. So with that, right, you just learned possibly 2 new things on this slide. You learned that, that negative b over 2a is going to help you find your minimum or maximum point of a quadratic, right? And then you learned to not fall into the trap of plugging in acceleration straight into the quadratic formula. So there you go. 2 birds with 1 stone. So the next problem. A student at the top of a building of height h throws a ball upward with a speed of vi, and then throws another ball downward with the same initial speed vi. How do the speeds of the two balls compare to when they each hit the ground? So it looks like I made a little bit of a typo there. That should be balls. Compare it when they each hit the ground. So if you want to try this for yourself, go right ahead. Otherwise, if you want to enjoy the show, I'll keep on going. Okay, so I just threw up some math. This is one of the things where it's like, oh my gosh, math. Okay, don't panic, right? The math is only as good as the explanation behind it. Okay, so what do we got going on here? So first off, we're going to start with the downward ball. Okay, so this is the ball that you have, and you just throw it straight downwards. Okay, straight down to the ground. So we have our v squared final of the ball thrown downwards is equal to the initial speed squared plus 2 times the acceleration of your final position minus your initial position. Okay. So in this case, right, your y final is equal to 0, and your y initial is equal to h. Okay. So keep that in mind. That's why we have a negative h. Our acceleration is negative g. Okay, so g on its own is equal to 9.8. Oh boy, that's a really bad 8. That is an even worse 8. Oh my gosh. Okay, 8 meters per second squared. So that is the acceleration due to Earth's gravity at the Earth's surface, approximately. And since the acceleration is downwards, we're going to plug that in as negative, right? So if you take a look at our situation, right, we are starting up here at some place at some height h, right, and we have g is pointing downward. So we're going to plug in a negative for that, right? And since our final position is 0, right, we actually go a negative displacement downwards. Okay, so we got two negatives there, right? If we simplify this, right, we get to our expression here for the final velocity. Okay. So then we're going to move to the upward ball. Okay, so we got the final velocity of the upward ball squared is equal to the initial velocity squared plus 2a, all that good stuff. Our initial position is still h, and our final position is the final position of the ball. Is the final position of the ball. Okay. So what I decided to do is I decided to break this into a couple of parts. Okay, so when you throw the ball upwards, right, it's going to start up here at some height h, right, and that's going to go up to some point up here, right, and then it's going to come back down. Okay, so what we have to do is we need to find information about how high does this ball get. Like, what is this? We'll say that's hf, right? Like, what is this final height up here? Okay. One important thing to note is that the maximum height corresponds to when our velocity is 0. Okay, so if you throw something straight up, okay, whenever the velocity then gets to 0 up at the top, okay, that is the maximum height that's going to reach, because then it's going to start falling back down with negative velocity. Okay, so our hf is really this variable right here, yf of d. Y sub fd. So we solve for that, right? So we can figure out the maximum height is this expression right here. Okay. And so then what I did is, instead of just going all the way down to the ground, right, is I cut it off right here. And so the next part that I'm going to do is going from the maximum height back to our starting height. Okay. So what we have here is our final velocity at the start is equal to the initial velocity, is equal to our initial velocity of the second part. So our final velocity of the second part squared is equal to the initial velocity of the second part squared plus 2a y final of the second part minus y initial of the second part. So the initial position, right, is this right here. Our final position is our original height h. Okay, it's not 0. It's our original height. So we're going back to the same height that we started at. We got our negative g here for the acceleration. And our initial velocity, right, since we were at the top at our maximum height, the final velocity, the velocity there was 0. So you plug things in and you simplify it, and you get a startling result. Is that the final velocity at the start, as we are going back down, is equal in magnitude to the initial velocity that was thrown upwards, except it's in the opposite direction. Okay, that's what the negative sign means. Is that the velocity is in the opposite direction that it originally was, but it's still the same but it's still the same number. It's just negative. So what does that mean? Well, it means that we can just go back to the downward ball problem. And that, well, we're just solving the same downward ball problem again now, right? Because, well, the velocity that we threw it down with, right? For the downward ball is now the same velocity that we now have for our upward ball as after it came back down. So as it's coming down, it's behaving the exact same as the downward ball. So that is another important result, right? First we showed, okay, when the maximum height of the ball occurs when the velocity is 0. And then we also showed that if you throw a ball upwards, right, when it passes you again on the way to the ground, it is going to have the same magnitude of velocity, but it's just going to be in the opposite direction, right? So instead of the velocity being up when you threw it up, when it comes back down, it's just going to be going at the same velocity but downwards. And in case you don't believe me, I ended up just taking our height here, right, and plugging it in, just going straight back down to 0, right? And oh, lo and behold, you get vi squared plus 2gh. So you still get the same thing. So that's definitely a conceptual thing that you want to remember, right? The maximum height occurs when your velocity is 0, and that is definitely an important result. Okay, so next we have one ball is dropped from a window and hits the ground with speed v. Another ball at the same time is thrown upward with speed v. Do these balls A, collide at the midpoint, above the midpoint, or below the midpoint? Okay. So what I ended up doing for this one is I ended up pulling out Mathematica, right? And yeah, I just want to make sure that everything else on this slide. So here's what I did is that I ended up defining a function for the upward ball, right? So we have our function here for the upward ball, right? Which is -1/2 times g times t squared plus g of t total times t. The reason why I had to do this g of t total thing, right, is because you need to know the final velocity in a numerical sense in order to get a visualized representation of what's going on. So right, so up here, right, I just defined what g is, and I defined what our total time is going to be, and this is the total time to hit. So this is like, so right, like this is the orange one is the downwards ball, right? So at 10 seconds, right, that's when it hits the ground, right? So that's our total time. So we have our this top equation, right? I needed because I need to plug in what the value of this is at 10 seconds. Here I need to plug. Whoops, that's just. I need to plug in this function right here. So because the downwards function, right, you start up at some height h up here, right, and I need to know what that height is. So right here is the downward ball equation, right, right here. And so then what I ended up doing is I just plotted it, right, and I plotted the intersection point and I plotted the midpoint. Okay. So in order to find where they intersect, right, you can just set the two equations equal to each other. And it turns out that they intersect at time t equals 5 seconds, which is halfway through our journey. Which makes sense, okay, right? You drop something, right, and then you threw something back up at it, right? And because one of them was thrown upwards at speed v and one of them ended up with downwards at speed v, right? They hit each other in the middle, okay? Or at least middle in time. I should say middle in time, right? So then if you plug t equals 5 into one of our equations, you get 367.5. So when you plot that, right, that's the green line right here. But that is above the halfway point of distance-wise. So the answer to this is that it is above the midpoint where these balls are going to collide. And so you're thinking like, okay, well, you did a lot of math here to get to this, right? Is there a quicker way to get to this answer? And the answer is, well, yes, there is, right? And it has to deal with, okay, you dropped one ball, right? So this ball has no initial velocity, right? It has to start accelerating and start moving, right? But the ball that you threw upwards, right, has a lot of velocity, right? It is gradually is slowing down, right? So you can see right in the blue one, it's gradually slowing down, right? It's leveling off. But the orange ball rate is continuing to accelerate and is getting down faster, right? And so what this means is that your two balls are not traveling. They're not traveling at the same speeds, at least when you start, right? And so since the ball going upwards has a lot more velocity to start with, it's going to be able to travel a much greater distance than the ball that had no velocity. And so they are going to hit each other above the midpoint because you started with extra velocity here when you threw it upwards. So that's a conceptual way to think about it. But I think that the visual representation here, right, is also helpful, right? Being able to visualize what's going on in the problem is also quite useful. So next problem. The driver of a car slams on the brakes when the driver sees a tree blocking the road. The car slows uniformly with an acceleration of negative 5.6 meters per second for 4.2 seconds. The car travels 62.4 meters before hitting the tree. With what speed did the car strike the tree? So if you want to try this on your own, go ahead. Otherwise, if you're going to enjoy the show, we'll keep going. Okay, so some more math. So what we know is that we have our final velocity as a function of initial velocity, acceleration, and distance. But we also have our final velocity in terms of initial velocity and acceleration with time. Okay. So what we can do is that we can rearrange this equation on the right and solve for our initial velocity. And then with our initial velocity, we can plug that back in up there. So this is how we get our expression down here in the second line. You then have to expand this out, this square out, right? So you get vf squared plus a squared t squared minus 2at v sub f. And then we go ahead and we do some algebraic steps to get v of f as a function of known stuff, right? We know the acceleration, negative 5.6 meters per second squared. We know the displacement, 62.4 meters, and we know the time, 4.2 seconds. Okay. And so the nice thing about Mathematica, right, is that you can just set up variables, right? You can set up a, you can set up t, and you can set up d, right? Our three known quantities, right? And then you can just plug in your expression, right? A squared t squared plus 2ad over 2at, right? You can just plug in your expression that you got, right? And since you defined what each of your variables are, you can use n, which just means give me a numerical answer, right? Sometimes Mathematica can be finicky, as it very oftentimes is, and it'll just give you back out your expression that you put in, and it's like, well, hang on, I wanted a numerical answer. So you tell it to give you a numerical answer, and it comes out to about 3.1 meters per second is the speed at which the car hit the tree. I don't know what that is in miles per hour. I suppose I maybe could have done the conversion. I think I might actually. If I remember, I'll put the miles per hour up in the corner here. Otherwise, if I forget to do that, you can run the conversion yourself and see what you get. Would the person have? Was this a low speed incident? Or was this a high speed incident? Or would the driver have lived, or would he have not have? I guess it's up for you to decide. So the next problem. The height of a helicopter above the ground is given by h equals 3t cubed. At t equals 2, the helicopter releases a small mailbag. How long after its release does the mailbag reach the ground? So if you want to give this a try, go ahead. Otherwise, if you're enjoying the show, we'll keep going. So, first thing we need to do is that we want to figure out what the height of the helicopter is, right? And so at t equals 2, that is 24 meters, okay? The other thing that we need to know is we need to know the velocity of the helicopter at t equals 2. Okay. So we take the velocity of c, the velocity of the chopper, at dh dt, which is 9t squared. And at t equals 2, that is 36 meters per second. Okay. So you might be wondering, well, why do we need to know what the speed of the why do we need to know the speed of the helicopter? Well, we need to know the distance, right? Because it says how long after it's released does the mailbag reach the ground, right? So if the helicopter is rising up off the ground, right, and then we're gonna drop the mailbag, right? Well, we now need to know how far that is off the ground. The reason why we need to know the velocity is that, well, the helicopter is moving, right? And the bag is attached to the helicopter for those 2 seconds, right? So the bag is also moving. So when the bag is dropped, the bag has velocity, okay? Like, for example, right, if you think of it, if you're in a car, right, and you're moving, right, well, you're moving at the same speed as the car, right? So if you then throw something out the window of your car, right, well, it has the same velocity as you do, and once you throw it out the window, well, now it's no longer attached to the car anymore. It's not part of the car anymore. So it's going to no longer be accelerating or moving along with you, right? That's going to start feeling air resistance and other forces, and it's going to appear like it just went straight back, right? So you need to account for the fact that there is velocity, that there is velocity of the mailbag as it's being released. Okay. So this is something that people will often forget. This is a way that teachers and professors and people who are giving you exams can trick you. And that people will often forget that the mailbag has an initial velocity. So don't forget about that. So we have our good old handy dandy equation right here that we've used a few times already. We know that acceleration is negative g. We have our initial velocity, 36 meters per second squared. 36 meters per second, not squared. Keep in mind that the velocity is positive, right? Because the helicopter was going upwards. So that is positive velocity. So do keep that in mind. And then the delta d is minus 24. Keep in mind that our final position is 0. This is final. Minus 24, which was our initial. Okay. So we set this equal to 0, right? And we're gonna use the quadratic formula to solve for this, right? Again, remember what I said is that this is the a coefficient, right? The whole thing you gotta multiply by the 1/2. Don't forget about that. The reason why you don't see the 1/2 down here, right, is that you have a 2 down here, right? So that does give you some leeway, right? And that you can forget about the 1/2 and kind of get away with it. But better be safe than sorry. So I intentionally did leave out the 1/2 because you were multiplying it by 2. You plug in all of your good stuff and you get your 2 solutions. Okay. But I get 2 solutions for time. How does that make sense? Which one is the right answer, right? Well, it's a 7.96, right? In this context, right, it doesn't really make sense to have a negative time, right? So that we ignore that solution. Okay. Keep in mind that it said how long after its release, after the bag's released from the helicopter, does it hit the ground? So the helicopter goes up, right? And then it drops it, right? So we're measuring from when it was dropped to when it hit the ground. Okay, that is 7.96 seconds. If it asked you how long after the helicopter took off does the mailbag hit the ground, well, you got to add on the 2 seconds, right? And that's going to be 9.96, right? So do keep in mind that if it wanted from when the helicopter took off, right, you have to add on the extra 2 seconds for that. So the context of the problem does matter. So don't forget about that. Next up, we have the time rate of change of acceleration is called jerk. Assume an object moves along the x-axis such that the jerk j is constant. Find expressions for the object's acceleration, velocity, and position, and then show that the squared of the final acceleration is equal to the initial acceleration squared plus 2 times the jerk times the change in velocity. So if you want to try this yourself, go ahead. Otherwise, if you're here and enjoy the show, we'll keep going. Bam! I know it's a lot of math, but hang on, we'll break it down. So jerk is defined as the derivative of acceleration with respect to time, okay? Or the second derivative with respect to velocity, or the second derivative of velocity with respect to time, or the third derivative of position with respect to time. So we're basically doing the derivations that we did previously, just we're adding another like layer onto it, right? So like you can solve the differential equation, right? And you get this down here, right? The steps are again similar to a couple of derivations we've already done, right? And the equation form is pretty similar, right? We have a quantity times the time plus some initial is equal to the final. Okay, then we can go over to the next one, right? We can use our previous result to get our next one. This one also looks pretty familiar, right? We have a 1/2 out here times the quantity, t squared, plus some initial quantity times t, plus some other initial quantity is equal to the final of some other quantity, okay? And then we can use this result again to get our position, right? And so this one again is a little bit more involved. Keep in mind that for these, right, j is a constant. Do not forget about that. Otherwise, we'll run into problems when you're trying to do these. So we do get something new out of this, right? We get this t cubed times 1/6, right? Because we had a third derivative with respect to time in this case, right? So the reason why I put this problem in here, right, is not just to make you do tedious derivations of math all over again, right? But it is to show you, okay, you have this right here, right? And so one thing to think about, right, is, well, what if I did the derivative with respect to time of the jerk, right? And I got some other quantity, right? How would these equations change, right? And does this go on indefinitely, right? And the answer is yes, right? You can keep taking derivatives with respect to time, right? And as long as you leave your highest order derivative equal to a constant, you can keep deriving equations of velocity, acceleration, position, and other and another higher tier derivatives up until the one that is constant. And you'll have greater and greater powers of t, and you'll have smaller and smaller coefficient powers. I guess an extra challenge problem is if you're interested in that, right? Is there a general form to this, right? Like as I add more and more higher order derivatives, right, and I get higher in order powers of t to the n, right? What do my expressions look like? So if you want to try to come up with that, you absolutely can. Definitely not required, but that's definitely something that you can think about. Then over here on the right, I wanted us to derive the squared expression over here, right? Again, it's pretty similar to the one that we have with velocity and position and acceleration. And you plug in things, you simplify them, right? And you end up getting down here. Nothing particularly earth-shattering or sharing about that one. So next problem. Two students on a balcony at distance h above the street. One throws the ball vertically downward at speed vi, and the other throws the ball vertically upward at speed vi. Find the time interval between when the first ball strikes the ground and the second ball strikes the ground, and how far apart are the balls at a time t. Okay, so if you want to try this on your own, go ahead. Otherwise, if you're enjoying the show, we'll just keep going. Let's see here. Let me just double check something. Okay. Okay, so how I did this, right, is we have ball one, the ball that's thrown downward, right? So you have your negative 1/2 gt squared, sub 1, right, for ball one, and you start at some initial height h, or your change in height, is h. And so then in order to solve for the time, right, you got to plug it into the quadratic equation. Okay. Ball two, same dealio, right? Except instead of the velocity being negative, because with ball 1 you throw it downward, right? We have an upward velocity, so the velocity is positive. And you go through and you solve and you put it in a quadratic formula. So then you just subtract the 2, right? Keep in mind that this is like a big huge quantity, so you got to distribute in the negative, right? So this becomes a positive, this becomes a negative, right? And so then when you get down here, the big square root things cancel each other out, and you then add your two like terms together, so you get 2v naught over g. Cool. Okay. But then, how far apart are the balls at a time t? Right. You can just subtract the the equations that you have. So you got the ball 2 upward minus the ball 1 downward, right? And you have to distribute in the negative, right? So this becomes a positive, this becomes a positive, and this becomes a negative, right? So the h's go away, and then these ones also go away, and you're just left with a positive v naught plus a positive v naught, and you get 2 v naught t. So I guess not a whole lot to say about this. It is just kind of purely mathematical. I guess like the distance thing is kind of interesting, and that doesn't depend on your initial height, right? It just depends on the initial velocity at which you threw the balls at, and that the distance over time continues to get greater and greater and greater until they hit the ground. So next question. 2 objects, A and B, are connected by a rod of length L, as shown in the diagram. Object A moves to the left with a constant velocity v sub A. Find the velocity of object B in terms of the angle, theta. So if you want to try this on your own, go ahead. Otherwise, if you're enjoying the show, we'll keep going. So right, we got our angle theta over here, right? We got our ball A moving to the left, right? I think I used distance A and distance B here in this problem. So we'll do A and B. So I said we were doing one-dimensional motion, so what's going on here? Well, we have since these things are connected by rod L, right? That kind of helps things out a little bit. But also is just, to me, a neat example, and I know when to show it, right? So the thing that you got to keep in mind, right, is that a squared plus b squared is equal to L squared, right? This is a right angle right here. So what does that mean? That means that b is equal to the square root of L squared minus a squared, right? You know, solve just rearrange these variables. But then what we need to do, right, is we want to find the velocity of object B in terms of the angle theta. So in order to do that, we want to take the derivative with respect to time. That's going to give us the velocity, okay? The key part about this, right, is that you have to implicitly differentiate your expression, okay? You have to, right, so you have B, right, so you have dB dt, right, but your A also has a time dependence, right? Like your distance A is a function of time, and your distance B is also a function of time, right? So you need to take that into account, right? And so that's why you have to implicitly differentiate things. You could have implicitly differentiated up here. I didn't. So if we do an aside over here, right? We got our expression, right? So the inner function, right? We're gonna have to use the chain rule. So our inner function, L squared minus a squared. Our outer function is the square root of I. So di dt minus 2a dA dt. And then the derivative of the outer function, right, is 1 over 2 is 1 over 2 times the square root of I, right? And then you do the chain rule, right, and you get this right here. And I'm now realizing, wait, why do I have? That should be negative. That should be. Why did I drop the negative? Well, let's keep going and see if I can see why I dropped the negative. But you can cancel out the 2's, right? And you end up with this right here. And so then you plug that in up here, right? And so what you okay, I know I dropped the negative, right? Because since we're going to the left here, right, we have v sub a, right? This dA dt, right, is v sub a, right? So since the velocity is negative and we have this negative sign, I just went ahead and made both of those positive. So then I plugged it in over here, right? And if you think about it conceptually, right, the velocity of b, the velocity is going to be going upwards for b, right, as this one comes inwards. So it needs to be positive, right? And the rationalization behind that is that. So you could leave the negative there, right? Because the velocity of b is in the opposite direction of the velocity of a is, but I just wanted to simplify things a little bit, so that's why I did that. So we can plug this in up here. So then how in the hell do we get cotangent? What is going on here? Well, we know that dA dt, right, this is equal to v sub a, right? So that's right here. Then we have a over the square root of an L squared minus a squared. Oh boy. Okay. Well, we know what L squared minus a squared is. That is b, right? So you can plug that back in. A over b. Okay. Well, if you remember that tangent of theta, right, is in this example equal to b over a, right? But instead we have a over b. So instead we use cotangent instead. So yeah. So the velocity of b is va times the cotangent of theta. So I just thought that was a neat result, so I figured I would share it. Okay, moving on to our last problem here. I know it's been a long video, so thanks for sticking around. We got one last example here that I thought was interesting to go through. So a commuter train travels between two downtown stations. The train starts by accelerating at 0.1 meters per second for a time t1. The train then brakes and accelerates at negative 0.5 meters per second squared for time t2. The total distance the train travels is 1 kilometer. Find the total time it takes the train to get to the second station. So the reason why I found this one interesting, right, is that this is a lot closer to a real world scenario, right? In that, you are in a car and a train or whatever, right? Even a plane, this is what it applies to, right? And that you accelerate to a maximum speed, right? Now in this example, the speed doesn't level off. We don't really we don't move at a constant velocity. But normally you'll accelerate, you'll reach a peak velocity, you'll travel at that peak velocity, and then you have to decelerate, right? So that's why I think that this is a good example, right? In that you have to deal with the acceleration portion, and then you got to deal with the decelerating portion. So if you want to try this on your own, go ahead and try. If you're just here to enjoy the show, here we go. So what's happening here is that we should move this thing out of the way. So we say that delta t is equal to t1 plus t2, and we know that the 1 kilometer is equal to d1 plus d2. Okay, so the distance d2 is the distance we travel in time t2, and the distance d1 is the distance we travel in time t1. Okay, so we know that d sub 1, the same d sub 1 from over here, right? 1/2 the acceleration of the first part, which is 0.1, times t1 squared plus the v naught of the first initial times t1 plus d naught 1 is equal to, and then that's just equal to this, right? Because this is 0, and this also goes to 0. Okay. So that's for part 1. That's for delta t1. For d2, right? We have 1/2 the acceleration of 2 t2 squared plus the initial velocity of 2 t2 plus the initial position. Okay. In order to find the initial velocity here, right? We need to use we get that from taking the acceleration of the first part times t1 plus the initial velocity of this. Again, right, this is 0. So we just get a1 t1, right? And you can then plug that in back up here, right? So then we end up down here with that plugged in, okay? So then what we do is we have d2 plus d1 is equal to 1 kilometer, which is equal to our expression here and our expression right here. And you just combine the two. And so I want to find, and then we know that the final velocity of the entire interval. So the final velocity at the end of our second time is 0. Okay, and so we have our expression, right? We have our generic velocity from acceleration expression, right? We know that so we know what v naught 2 is, right? We had that right. We had that back up there. So we end up getting this right here. And what we can do is we can solve for t1. Okay, so from this expression, right, we can rearrange it and we can solve for t1. Okay, you could rearrange it and solve for t2, but I did t1. And so once you know what t1 is, right, you can end up plugging t1 back into our expressions back up there. And so when we cycle it back down in here, right, we get our 1 kilometer is equal to a big honky thing, right? And so at the end of the day, this is a quadratic. You can collect your t underscored 2 terms, right? Your t squared terms. Actually, all of them, it looks like, are, yeah, you got the t there, a t sub 2 there, a t sub 2 there. But anyway, it was more work than I wanted to do, right? You can go ahead and do it by hand, right? But I've got a handy tool called Mathematica that allows me to skip some of the algebra work. So again, I just defined variables a1, a2, and then I set what t1 is equal to, right? I didn't want to plug in this big, huge, oh, my cord is getting tangled. Okay, there we go. So I had, right, this big, huge expression down here. I didn't want to type that in, right? It's a lot easier to type in this expression right here, right? So I typed in that expression right there, and I just set what t1 was equal to, right? And you again, we want a numerical answer. We don't want a symbolic answer. So yeah, keep that in mind. We want a numerical answer, and we want to solve. So we said 1,000, right? 1 kilometer, 1,000 meters. Is equal to our big, huge, long expression here, and then we want to solve for t2, and voila, right? We ignore the negative one, and we get our time t2, which is about 25.8 seconds. And then since we defined t1 in terms of t2 up here, right? Once we know what that is, we can just type it in, and that gives us 129.1 seconds, and then we can figure out the total time it takes to get to the station, which is about 155 seconds. Okay, so about 2.5 minutes. Is 150 seconds is 2.5 minutes. So yeah, that is cool. So that is going to do it for me in this episode. I know it was a long one. There was a lot of examples that I wanted to show. So in the future, I'm going to try to reduce the number of examples that I show, and try to highlight things a little bit better. But I just really liked some of the problems, so that's why I went through so many. But thanks for tuning in. Thanks for watching. You know, if you can subscribe. If you have any questions, you can leave a comment. You can also email me if you have a question. Right. I don't like typing math into the YouTube comment section. That could be pretty tedious. So if you have like a super mathematically intensive question, sending me an email is probably better, so I can type it out in a type editor and send it back to you in a format that's going to be easier to understand and easier to read. So again, thanks for watching. I hope you learned something. I hope you learned something interesting. I hope you learned something new. Maybe got a little bit of a different perspective. And so until next time, I will see you in the next episode.